And everyone should be able to see the screen, Air Conditioning Diagnostic Module 3. Jill, can you see the screen okay?
Yep, I'm good.
Alrighty. Okay, well, I've got 2 o'clock at the top of the hour. Let's go ahead and get started today. So today we're going to be doing Air Conditioning Diagnostics Module number 3 and 4. And again, I'd like to welcome everybody to the program today. We will be learning some diagnostic procedures for both 410A and R22 air conditioning systems. Now, some of our key learning objectives today will be as follows. We're going to go ahead and review the saturation pressure temperature chart that we talked about in Module 1 and 2. We'll review superheat charging chart and do a little bit of practice just to remind everybody how to utilize that chart. We're going to dig into superheat and the evaporator coil, and we will have some practice sessions, as well as subcooling in the condenser coil with practice sessions. Now, team, one of the things that we're going to do today, this is going to be fairly interactive, so please go ahead and mute your microphones, but when we get to the point where we're actually doing some practice sessions, go ahead and unmute your mic, and I'll ask some pointed questions and some guiding questions, if you will, and then we can all kind of participate on the recording today if that's okay with everybody. So the first thing I'd like to do, kicking this off again, now this is actually out of Module 1 and 2, but saturation pressure temperature chart practice. Just to make sure everybody is comfortable using the pressure temperature chart, go ahead and take your pressure temperature chart out and find the 410A section of it. You'll notice on one side is 410A, some columns. They'll be kind of color-coded, 410A. And then on the other side of the sheet, your handout, you'll have some R22 pressure temperature conversions. So go ahead and unmute your mic, everybody, and let's go ahead and do some practice together as we take a look at the pressure temperature chart just as a quick review. So starting out with the 410A section of your chart, let's find 55 pounds of pressure, PSIG, and convert that to temperature. So somebody help me out at 55 pounds of pressure for 410A. What's the pressure temperature conversion off the chart, please?
5.
Excellent. 5 is correct. And let's go ahead and do a few more. So at 130 PSIG, 410A, what is the pressure temperature conversion, please?
45.
Okay, good, excellent. And at 265, what's the pressure temperature conversion?
88.
Go ahead, someone said it, go ahead and say it again.
88.
So that's close enough. Now remember, team, if you're within 1 or 2 degrees or 1 or 2 points, that's plenty close for field work. The other thing I'd like to remind everybody when we're looking at the pressure temperature chart, what we're really trying to find is we're trying to find the temperature with which the refrigerant is changing state inside the coil. So another way to think about that, the hot gas in the condenser coil is turning back into a liquid at that pressure temperature conversion. Likewise, in the evaporator coil, the refrigerant inside the evaporator coil is boiling from a liquid to a vapor in the evaporator coil at that pressure temperature conversion. So kind of be thinking about that as well as we take a look at the saturation pressure temperature chart. So let's do another one at 375 PSIG. At what temperature is the hot gas turning back into a liquid in the condenser coil? Anybody?
112.
Excellent. And how about at 455 pounds of pressure, at what temperature are we changing that hot gas back into a liquid in the condenser coil?
127.
Perfect. Excellent. Any questions or comments on that so far before we do a couple of R22 practice sessions as well? Is everybody good?
Yep.
Okay. R22, find the R22 section of your chart, please. And let's take a look at 35 pounds of pressure. 35 pounds of pressure. At what temperature is that liquid refrigerant that we sprayed into that evaporator coil past the metering device? At what temperature is that refrigerant boiling off or turning into a vapor in the evaporator? Okay, good. That sounds right. 13 degrees. How about at 68 pounds of pressure? At what temperature are we boiling that refrigerant in the evaporator?
40.
About 40 degrees. Excellent. Now remember, team, if you're within 1 or 2 degrees of the chart value, that's close enough, because sometimes you'll see on some pressure temperature charts, it might be a fractional number or a decimal. It might be, 49.2 or something like that. So it's perfectly fine to round up or round down. If you're within a degree or so of the chart value, that's plenty close for field work. How about 85 pounds of pressure for R22? What's the pressure temperature conversion at 85 pounds of pressure?
51.
Excellent. Good. How about 230 pounds of pressure? In other words, at 230 psi on the high side, at what temperature are we converting that, or are we changing that hot gas back into a liquid in the condenser at 230 pounds of head pressure?
111.
Excellent. And then finally, at 325 pounds of pressure, R22, at what temperature are we changing state inside that coil?
137.
Close enough. Excellent. Is there any questions or comments, anyone, on the saturation pressure temperature chart and what it's really telling us as far as the temperature that we're changing state inside the coils?
No.
Everybody good?
Absolutely.
All right. Well, excellent then. Well, the next thing we're going to talk a little bit about, team, is we're going to go ahead and review. Now, we did cover this chart in the module number 1 and 2, but let's just review it real quick for today just to make sure everybody's squared away. So again, as you're taking a look at the superheat chart, if you look at your handout, you're going to notice in the upper quadrant, or the upper part of the chart itself, it says the diagonal lines represent indoor return air temperature. Now all the blue numbers are dry bulb numbers, and all the red numbers are wet bulb numbers. You'll notice that those blocks are going to be associated with a diagonal line. On the left-hand side of the chart, if you see a 95, 79, 85, 71, etc., those green blocks correspond with a diagonal line. So as we take a look at those diagonal lines, that's actually return air, indoor return air temperatures that we're looking at that are associated with those little green blocks to the left-hand side. Now, when you use a dry bulb and when do you use the wet bulb numbers is going to be relative to the relative humidity in the space. So if the relative humidity in the space of your return air, and of course you're going to have that sling psychrometer, remember, that we talked about to find relative humidity as well as wet bulb temperature. But if the relative humidity is above 70% or it's below 20%, we're going to use those red wet bulb numbers. However, if the relative humidity is in between 70 and 20%, for instance, let's say it's 55% relative humidity in the space, we'd use the blue dry bulb numbers. You'll find at the very, very bottom of the chart, there's some numbers down there, 60, 65, 70, all the way up to 110 degrees. That represents outdoor air temperature on the chart. And then on the left-hand side of the chart, on the far left-hand side of the chart, you'll see some black numbers going from 50, 45, all the way down to 5 degrees. And what that is, that represents the required superheat under any condition of measurement of outdoor temperature and indoor return air temperature. So again, I want to stress this is a generic superheat chart, and it will only be used for metering devices on the indoor coil that are of the piston or the orifice type of metering device. You will not use this chart with an expansion valve. You'll only use this chart for a piston type of metering device. So, real quick review. Let's do an example together. Let's say it's 90 degrees outside. And so step number 1, we find the outdoor temperature at the bottom of the chart. And we see we have highlighted with the purple box there, we have 90 degrees. That's step number 1. So we have 90 degrees outdoor air temperature. We then find the corresponding diagonal line that represents the indoor return air temperature, wet bulb and dry bulb. Now, in this example, let's say, just for an example, I'm making this up, but let's say it's 50% relative humidity in the space. Well, and we measure with our digital or sling psychrometer, we measure a 67 wet bulb and an 80 degree dry bulb temperature. And so those can vary some based on the relative humidity, but let's say it's 50 degrees our 50% relative humidity in the space. So we'd use that blue number, and let's say our measurement was 80 degree return air temperature dry bulb. Well, we'd find that corresponding line, and we'd take it down until it intersects the outdoor temperature line that we, in step number 1. And where those two lines intersect together, you move straight to the left, and then you find the superheat that's required under those points of measurement. So another way of thinking about it is this. If my indoor return air temperature was 80 degrees, and I had a 50% relative humidity, which would allow me to use that 80 degree blue number, and my outdoor temperature was 90 degrees, if I move straight to the left, I see that my required superheat is 13 degrees. So in this example, if we had these conditions of measurement, in this example, we'd be looking for a target superheat with that piston on the indoor coil, on the evaporator coil, of 13 degrees. Now, team, remember, if you're 1 or 2 degrees from this, in other words, if it's supposed to be 13 and it's 12, leave it alone. It's close enough. If it's supposed to be 13 and it's really 14, leave it alone. You get the idea. Now, if it's supposed to be 13 and it's 5 degrees of superheat, then we have an issue. Likewise, if it's supposed to be 13 and it's 35 degrees of superheat, we have an issue. So you kind of get the idea. So if you're within a degree or so, just leave it alone. That's close enough for field work. Is there any questions or comments on the utilization of this superheat chart? Now please remember, team, again, this chart is strictly for piston type of metering devices on the indoor coil. Let me go ahead and clear the information off that chart, and let's do 1 or 2 practice sessions together. So go ahead and unmute your microphones for me, please. And let's say it's really dry outside. Let's say we live in Arizona, and it's hot and dry outside, and it's 105 degrees in Arizona. So find 105 degrees on your chart. We then take our return air temperature, and we see that we have 30% relative humidity. 30% relative humidity. So that automatically means we're looking for a blue dry bulb number. And let's say it's 80 degrees dry bulb in this example. It's out there in Arizona. It's 80 degree dry bulb. So find 80 degrees on your chart, 80 degree dry bulb, that's the blue number. Find that diagonal line where it comes down and intersects with 105 degrees outside. Now move straight to the left. What is the required superheat? Anybody? About 5 degrees. Now please note on the chart, team, that you never charge below that 5 degree line because we don't want to slug the compressor of refrigerant. So in that example, 5 degrees of superheat under those conditions would be about right. Let's do another one. Let's say we're over in Mobile, Alabama, where I live, and it's real humid outside. It's humid and wet outside, and it's 95 degrees outside. But we have 75% relative humidity in the house. And inside that house we have 71 degree wet bulb temperature. 71 degree wet bulb temperature. Because we have 75% relative humidity, we're going to use the red wet bulb line. And so in this example, let's say here in Mobile, we have a 71 degree wet bulb temperature. And it's 90 degrees outside. So it's been raining, and it's wet, and it's nasty outside, and it's humid. 71 degree wet bulb temperature, 90 degree outdoor air temperature. Under those conditions, team, tell me, what should my superheat be off the chart?
18.
That's close enough. Excellent. Any questions or comments on the superheat chart and where we would use this chart if the evaporator is utilizing a piston type of metering device? Okay, good. Well, let's go ahead and jump into some other things then today in our module 3 and 4. Okay, so we talked a little bit about superheat chart. Now let's talk about what is superheat. Superheat, team, is going to be the condition of the evaporator coil. Now please remember there's only 3 conditions the evaporator can be in. It can be flooded, there's too much liquid in there. It can be starved, we're not feeding enough liquid in the evaporator coil to get the job done. Or it could be normal. Now we find that if it has a piston on the indoor coil, on the evaporator coil, we're going to have to hit the superheat chart to find out what normal is off the superheat chart with a piston. Or if it has an expansion valve on it, please write this down or make a note on this page. Superheat with an expansion valve should be about 10 to 15 degrees under normal running conditions. Now, superheat on the expansion valve, that TXV is going to maintain a superheat. It'll fluctuate and open and close to maintain a superheat. So normal would be considered about 10 to 15 with an expansion valve. However, if we have a piston, we learned a minute ago with our superheat chart, if we have a piston, we have to look at the superheat chart to determine what's normal. So again, there's only 3 conditions that evaporator coil can ever be in. It can be flooded, there's too much liquid in the coil. Starved, not enough liquid in the coil. Or normal, based on the superheat chart with a piston, or about 10 to 15 degrees of superheat with an expansion valve. Now, team, to measure superheat, what we're going to do, we're going to convert suction pressure to temperature, step number 1, just like we were doing in practice a little bit ago with our pressure temperature chart. So step number 1, we convert suction pressure to temperature. Step number 2, we're going to clamp on with a good high-quality digital thermometer and temperature clamp. We're going to clamp onto the suction line at the outlet of the evaporator and read the temperature of the suction line. Step number 3, we're going to compare the temperature that we got off the pressure temperature chart and number 2, the physical temperature of the suction line, and we're going to find the difference between those 2 temperatures. The difference will be your superheat level. So one more time, we convert suction pressure to temperature. Step number 1. Step number 2, we clamp onto the suction line and we measure the temperature of the suction line. Step number 3, we find the difference in those temperatures, and the difference will be our superheat level. Now write this down or make a note of this. If the superheat is low, in other words, we have a low number, let's say it's an expansion valve and we're looking for 10 to 15, but we have 5. If the superheat number is low, that means that evaporator coil is flooded full of liquid. If the superheat number is high, it means the evaporator is starved of liquid. If the superheat is normal, it'll be about 10 to 15 degrees with an expansion valve, and then superheat chart value that we practiced a minute ago if it has a piston on the indoor coil or an orifice on the indoor coil. So any questions or comments on superheat and what it's telling us about the evaporator before we do some practice sessions? Okay, I'll tell you what, let's go ahead and take a look at our refrigeration graphics here. We notice right in the middle of the screen we've got a suction gauge and we have a liquid pressure gauge as well. And the suction gauge is on the left and it's circled by blue. And the liquid pressure gauge is on the right and it's circled by red. We also notice, as a quick review from our Module 1 and 2, if we have a white background on those gauges, we automatically know it's an R22 call. So you'd look at your R22 pressure temperature chart. If it has a pink or a rose-colored background, we automatically know that those gauges will be indicating a R410A call. Now, as we take a look at the refrigeration graphics, take a look at your compressor. Find the compressor on the screen in the lower left-hand corner, and follow along with me as we review the refrigeration graphic real quick and what we're looking at. We see we have a hot gas line coming off the compressor to the outdoor coil, where that hot gas will be turned into a liquid. We then have that liquid coming out of the outdoor coil, passing through a filter dryer, down a liquid line to a TXV. The TXV is then spraying liquid refrigerant into the indoor coil, where it will boil off and turn into a vapor. We then have that cool vapor coming down the suction line back to the compressor. Now you'll notice there's some green blocks by the indoor and the outdoor coil. Those are temperatures of the air going across those coils. As an example, on the outdoor coil, we see we have an outdoor dry bulb temperature of 91 degrees. That's the temperature of the air going across that outdoor coil. On the indoor coil, we have an IDWB, that's indoor wet bulb temperature of 70 degrees. On the indoor coil, we have an IDDB, that's an indoor dry bulb temperature of 84 degrees. And then we have an RH percent, that's the relative humidity, percent relative humidity going across the indoor coil. In this example, it's 49 degrees. 49%. Now, team, you'll also notice throughout the refrigeration cycle we have these yellow temperature blocks. The yellow temperature blocks will indicate the temperature of the lines and the components that it's measuring. To give an example, we've got 68 degrees going across both ends of our suction line. In addition, you'll notice at the top of the screen on the left-hand side we have 2 temperature blocks across the filter dryer. They are not active at this time because we're just doing superheat practice. Later on, we'll activate those temperature blocks in their entirety as we start doing diagnostics later on. You'll also notice there's also 2 temperature blocks along the liquid line from the outlet of the dryer to the inlet to the expansion valve, or TXV. That's the temperature of the liquid line in those 2 temperature blocks. So again, we will activate all those temperature blocks later when we're doing subcooling and when we're doing refrigeration cycle graphics, our refrigeration cycle diagnostics. But for now, we're just going to be doing some superheat practice. And so the only thing we're going to activate now is the suction line temperature and our suction pressure gauge. So in this example here, we see that we have an R22 service call. We have a white background on the gauges, and we have 82 pounds of suction pressure. So somebody, go ahead and unmute your mics. At 82 pounds of suction pressure, step number 1 for finding superheat. At 82 pounds of suction pressure, what's the pressure temperature conversion for R22 at 82 pounds of pressure? Anybody? Off your chart. About 49 degrees. That sounds correct. Now, the physical temperature of the suction line leaving the evaporator coil is 68 degrees. And so the difference between 49 and 68 is about 19-degree difference. Almost 20 degrees of difference. Now remember, team, on an expansion valve, our superheat should be between about 10 to 15, but in this example, the superheat is high. It's about 19 or 20, indicating that indoor coil has a condition of being slightly starved because the superheat number is high. So remember, team, if the superheat is high, for whatever reason, that indoor coil is starved of refrigerant, or it's getting starved of refrigerant for whatever reason. So in our example, we have elevated superheat, and the indoor coil is starting to be starved. Any questions or comments on that? Well, team, where we're going with this training is this. If we look at the condition of the coils, if the coil is, if the indoor coil is starved and the outdoor coil is flooded, that means something. And if they're both starved, that means something else, and so on. So by looking at the condition of the coil, we can always figure out what's going on in the refrigeration circuit. Let's do a couple more of these just to make sure everybody's got this. In our next example, we see that we have an R22 system, but this time we have an orifice or a piston type of metering device on the indoor coil. So before we determine if our superheat is high or low or normal at this point, because we have an orifice, we have to look at our superheat chart first. So let's do that. So as we take a look at this orifice, we see that we have an indoor wet bulb temperature of 71 degrees. We have an indoor dry bulb of 86 degrees and a relative humidity of 48%. So looking at your superheat chart, team, remember, if our relative humidity is below 70 or above 20, we use the dry bulb line. So in this example, we have a relative humidity of 48%. That gives us the blue dry bulb line. So find an indoor dry bulb off your superheat chart of 86 degrees or about 86 degrees. And then we have a 99-degree outdoor dry bulb temperature. Well, that's pretty close to 100. So if you just want to round it to 100, so find 100 degrees outdoor air temperature with about an 86 or an 85-degree indoor dry bulb. What should the superheat be? Anybody in that example? What should our superheat be? Off the chart. Anyone? Alrighty, let me tell you what, let me pull a superheat chart here myself. I've got one printed out. Get If everyone please give me just a moment while I do that, we'll do a little work together. So as we take a look at this service call, the superheat practice, we have an indoor dry bulb of 86. Well, that's pretty close to 85. So I'm going to take the 85-degree dry bulb line and 99 degrees outside. And 99 is real close to 100. So I'm going to go 100 degrees outside with an 85-degree dry bulb. Looks like we need about 14 degrees of superheat. Does everybody agree with that?
Yeah.
Okay. All right. Now take your pressure temperature chart. Take your pressure temperature chart for me and find 88 pounds of suction pressure, R22. What's the pressure temperature conversion for 88 pounds of suction pressure?
$51.
Good, about 51. Good. Now, the difference between 51 and 54 degrees suction line temperature is only about 3 degrees. Is that correct? And so in this example, we know our superheat is low because our superheat chart said we needed about 14 with a piston, with an orifice. And we only have about 3 degrees of superheat. So for whatever reason, we have very, very low superheat on the indoor coil. So somebody help me out. If the superheat is low, is that indoor coil flooded, starved, or normal?
Flooded.
It's extremely flooded for whatever reason. Good diagnosis. Any questions or comments on that? Okay, well, let's do a couple more just to make sure everybody's got this. In this next example, we have 132 pounds of suction pressure, and this is on a 410A unit because we have pink colored background on the gauges. Now, we do have an expansion valve, a TXV, so an expansion valve should maintain a superheat of about 10 to 15 degrees. So we automatically know we're looking for a range of about 10 to 15 with the expansion valve. So somebody help me out on the R410A chart, pressure temperature chart, at 132 pounds of pressure. What's the pressure temperature conversion at 132 for 410A? Anybody? Step number 1. Anyone?
46.
Yeah, that sounds about right, about 46. So 46 degree pressure temperature conversion for 410A at 132 pounds of pressure. And then we notice that the temperature of the suction line leaving the evaporator is 55. So we're running about 9 to 10 degrees of superheat on that indoor coil. So at this point, would you consider that coil flooded, starved, or normal? If we're supposed to have 10 to 15 and we've got 9 to 10, what would you consider the condition of that coil?
It's close enough.
That's what I say too. Thank you for that great observation. Team, if you're within 1 or 2 degrees of your chart or your target value, that's close enough. And what I'd probably do on this service call, I'd just clean the coil good to make sure I had a clean air filter on the return duct and that sort of thing. And with 9 to 10 degrees of superheat, I'd leave it alone as well. Any questions or comments on this so far? So superheat always tells us the condition of the evaporator coil. Let's do another one quick. Here we have 127 pounds of suction pressure. 127 pounds of suction pressure, 410A. What's the pressure? Step number 1, what's the pressure temperature conversion at 127 pounds of pressure for 410A? What would the pressure temperature conversion be? Anybody?
Dylan there said 40.
Okay, that sounds about right. I don't have a chart in front of me. I'm letting you guys do this. I've got a superheat chart, but I don't have a PT chart, and I kind of deliberately did that to make everybody kind of answer the question. So about 44, does that sound right? Does that sound right to everybody?
Yeah, he's right.
Okay. And we see the temperature of the suction line leaving the evaporator coil is about 53. So in this example here, again, we've got about 9 degrees of superheat with an expansion valve. How do you feel about that?
Rinse off the coil. Have a great day. Change the filter.
Okay, there you go. That's what I'm talking about. Excellent. Okay, so is there any questions or comments on superheat before we jump off the screen? Is there any question or comments on superheat and what it tells us about the evaporator coil? Remember, team, if the superheat is high, the evaporator coil is starved for whatever reason. And we'll get to those reasons later on when we get into diagnostics. If the superheat is low, that means the coil is flooded full of refrigerant for whatever reason. And if the superheat is normal, we'll find normal off of a superheat chart if it's a piston, and then we'll just automatically presume about 10 to 15 with an expansion valve, because the expansion valve should maintain about 10 to 15 degrees of superheat under normal running conditions. Any questions or comments on superheat and what it's telling us about the evaporator coil? Is everybody good? Okay, well, we have 2 coils in the system, team, so let's take a look at the outdoor coil now, the condenser coil. And let's talk about subcooling. Now, subcooling tells us the condition of the condenser coil, just like superheat showed us the condition of the evaporator coil. Now, please write this down. This is really, really, really important. Make a little star or write it down in your handout or your workbook, your handout there on this page. Make a little star, put a smiley face, and so you remember this. Subcooling is opposite of superheat. Subcooling is opposite of superheat. And maybe some little parentheses concerning coil condition. So we learned earlier that if the evaporator coil, if the superheat was high, the evaporator is starved. It's exactly opposite with the condenser coil. With the condenser coil, if the subcooling is high, that coil is flooded. It's exactly opposite of superheat. So the condenser coil condition and the evaporator coil condition, high and low and normal and so on, are exactly opposite of each other. So on the condenser coil, if the subcooling is high, the condenser coil is flooded. If the subcooling is low on the condenser coil, the condenser is starved of liquid. It doesn't have enough liquid in there. And if the subcooling is about 10 to 16 degrees based on the SEER rating of the unit, there's lots of factors. SEER rating and line length and so on can affect subcooling, but for all practical 95% field application, if your subcooling is about 10 to 16 degrees, that will be considered a normal range. Again, based on SEER rating and some other factors. So normal subcooling is about 10 to 16, 12 to 15, somewhere in there, based on the line length and the SEER rating. And on the condenser coil, if the subcooling is high, that coil is flooded full of liquid. It's exactly opposite of superheat on the evaporator. If the subcooling is low on the condenser coil, it's starved or empty, which is exactly opposite of the evaporator. If we have low superheat on the evaporator is flooded. But if we have low subcooling on the condenser, that coil is starved. It's exactly opposite. Please make a note of that so you can remember that. Now, to find subcooling, we're going to do some very similar things that we did before. Step number 1, we're going to convert liquid pressure this time to temperature off of our pressure temperature charts. We're going to convert liquid pressure to temperature off the pressure temperature chart. Step number 1. Step number 2, we're going to clamp onto the liquid line outside by the condenser. And we recommend downstream of the service valve. Make sure the service valve is open all the way. Now in our graphics we show there's a dryer on the line downstream of the service valve. So based on your local codes or the type of equipment that you're looking at, you may have a dryer on the liquid line outside. Now, on all of our Champion equipment, what I really like is the fact that on all of our Champion equipment, our filter dryer is actually inside the cabinet. But either way, we want to make sure that we clamp onto that liquid line, step number 2, and actually measure the temperature of that liquid line. So step number 1, we convert liquid pressure to temperature off the chart, just like we did in practice and so on, off the pressure temperature chart. Step number 2, we're going to physically measure the liquid line temperature with our good high-quality clamp-on temperature probe. Step number 3, we're going to find the difference. And now the difference between those two temperatures is that's subcooling. And so the difference is subcooling. So if the subcooling number is high, that coil is full of liquid. If the subcooling number is low, the condenser is empty. If the subcooling is about 10 to 14, 10 to 16, based on the SEER rating of the unit, we'll consider that normal subcooling level. Any questions or comments on subcooling and what it tells us about the condenser coil? All right, team, well, let's do some practice together. So you'll notice as you take a look at the graphics now, you're going to notice that we've activated the temperature blocks along the liquid line circuit. So we see that across the dryer, in this example, we have 108 degrees across the dryer. We also have 108 degrees down the liquid line on both ends of the liquid line. This is actually great news. Now to find subcooling, step number 1, we're going to find we're going to take the pressure of the liquid pressure, or the high side pressure, off our liquid pressure gauge or high side gauge, and we see that we have a white background. So that tells us we have an R22 system. So referring to your R22 pressure temperature chart, go ahead and unmute your mics and let's do this together. So at 253 pounds of pressure, step number 1, what's the pressure temperature conversion of R22 at 253 pounds of pressure? Anybody off your pressure temperature chart?
118.
Sounds about right. And the temperature leaving the outdoor coil on the liquid line as it enters the filter dryer is 108 degrees. So the difference between 118 that we got off the pressure temperature chart and the physical temperature of the liquid line is 108 degrees. The difference between those is about 10 degrees. Now remember, team, normal subcooling is about 10 to 16 degrees based on the length of your line set and the SEER rating of the equipment. So the condition of that outdoor coil, in this example with 10 degrees of subcooling, would you consider that flooded, starved, or normal?
Normal.
About normal. Good. Let's do another one. In this example, we have 304 pounds of pressure, and this is an R22 call as well. We've got white color gauges, background on the gauges. So please, off your pressure temperature chart at 304 pounds of pressure, step number 1, what's the pressure temperature conversion at 304 off of the pressure temperature chart?
132.
132. Excellent. Now we notice that on the inlet of the filter dryer from the outdoor coil on the liquid line, we have 104 degrees on the yellow temperature block. So we see we take the difference between our step number 1 and 104 degrees. And so currently, what is our subcooling level in this example? What's the difference from the chart value to 104 degree?
It's flooded.
How many? Oh, I love that answer. We have a horribly flooded condenser because our subcooling is high. Good. Excellent. Now, team, again, this is where we're going with this training from refrigeration cycle diagnostics. We look at the condition of the outdoor coil, we look at the condition of the indoor coil, we look at our pressures, we look at our temperatures, and it becomes very, very clear on what's going on with the system. So that's what this Module 3 and 4 is all about, is really figuring out refrigeration cycle diagnostics. But the basis of our learning for this is going to be coil condition. If the outdoor coil is flooded and the indoor coil is starved, well, that means something. If both coils are flooded, well, that means something else, and so on. So by looking at coil condition and temperatures and pressures in the refrigeration cycle, we can diagnose systems ready for this, not in hours, but literally in minutes, if we understand this technique. So let's do a few more just to make sure everybody's got subcooling down really well. So in this example, this next example, we have a 410A unit. We have 407 pounds of liquid pressure. So step number one, let's find out the pressure temperature conversion for 407 off the off the R410A side of the chart. So at 407, what's step number one? What's the pressure temperature conversion? Anybody?
118.
Sounds about right. And we take a look at the temperature of the liquid leaving the outdoor coil as it enters the filter dryer. It looks like it's 99 degrees. And so what's the difference? It's also flooded. There you go. Any questions or comments on subcooling and what it tells us about the condenser coil condition? Okay. Let's do another 410A example. So in this example, we've got 332 pounds of pressure. And so referring to your 410A chart.
About 332.
Okay. And so what's the pressure temperature conversion?
101. So yeah, you're still flooded.
103.
Okay, so in this next example here at 332, the pressure temperature conversion was about 103. Is that correct? So somebody might have an open mic. I'm hearing some pretty strong feedback. How about now? Okay. All right. So go ahead. So at 332 pounds of pressure, what's the pressure temperature conversion for 410A?
So it'll be 103. The difference will be 2. So it'll be starved because it's low.
Excellent. There you go. So basically, anytime we have a low subcooling value, we've got a starved condenser coil. Okay, before we start Module 4, is there any questions or comments on what we did in Module 3 so far today? And so we covered superheat, we covered subcooling, we reviewed the pressure temperature chart, we also reviewed the superheat chart if we have a piston on the indoor coil. And so in this next module, we're going to be getting into actually doing some diagnostics. But before we go to Module 4, is there any questions or comments on the things that we just talked about? Anyone? Okay, well, welcome to Module 4 then, class. We're going to go ahead and jump into Module 4. And we're going to continue learning about diagnostic procedures for 410A as well as R22 air conditioning systems. Now, in this particular module, we're going to be reviewing a parameters page, and I'm going to ask you to make some notes on your handouts. We're going to review some diagnosing system problems page, again, making some notes on your handouts so you have them for future reference. And then we're going to actually do some interactive service calls in practice. And so this is really the fun part of the program, because now you get a chance to tie it all together, those things that we've talked about concerning pressures and temperatures and superheat and subcooling and all the stuff that we've talked about. So let's go ahead and take a look at some of our parameters. And this is our mechanical parameters for our air conditioning systems. So please make some notes of this. Make some notes on this page. If you have a unit with a TXV, and your manufacturer, this is kind of generic in nature, because some manufacturers, if you go out, you may find that they provide you a suction chart and a liquid chart. If they give you that chart, then by all means utilize it. We also learned, as a quick review, that a unit with a TXV should maintain a superheat of about 10 to 14 degrees if it's a TXV. We also found that normal subcooling for a unit is going to be about 10 to 14, 12 to 16 based on SEER rating and based on your line length. But for practice today, we'll consider 10 to 14 degrees of subcooling normal with an expansion valve. Now, team, if we have a unit with an orifice or a piston on the indoor coil, we found out that we're going to have to use a superheat chart. We're going to have to use that superheat chart and find that chart value if we have an orifice. In addition, again, if you get out on a piece of equipment and you're working with a manufacturer's piece of equipment that provides a suction pressure chart or a liquid pressure chart, please by all means use the chart that they provide. All the information you can get on a service call is always the best. In addition, a unit with an orifice, even though it has an orifice on the indoor coil, normal subcooling ranges are going to be still about 10 to 14 degrees if the unit is charged properly under normal nominal conditions. You're still going to be looking for about 10 to 14 degrees of subcooling will be considered normal even with an orifice. Now, if you don't have a manufacturer's chart for suction pressure and liquid pressure, please, if you do have the manufacturer information, go ahead and use it. However, if you don't, now this is something new that I've added to the program for our web-based training, but go ahead and make a note of this. Take a few minutes here to make a note. The approximate refrigerant pressures under nominal rated conditions for an R22 and a 410A system, you're going to notice R22 under rated nominal conditions, an R22 system should be running about 70 to 75 psi on the suction. Now, again, this is just strictly for your information. This isn't dyed in the wool. This isn't something you can put a stamp on. This is just 45 years of field experience on my part. So under rated conditions, an R22 system should run about 70 to 75 pounds of suction and about 195 to 230 pounds of pressure on the liquid side. And again, this is just strictly for your training today. So make a note of this. Write this down. Have this information handy when we start doing our service calls. It'll help you. An R410A system, normal suction range is going to be about 135 to 145 psi on the suction under nominal rated conditions. Now team, remember, this presumes you got clean coils, you have proper airflow, you got a clean air filter on the indoor unit and so on. The outdoor coil's clean and so on. Okay, so this is presumed the unit is well maintained and under nominal conditions. R410A liquid pressure typically runs about 330 to 350 psi, again with clean coils, proper indoor airflow, clean air filter and so on. So take a minute to write those down. These are approximate refrigerant pressures that we're going to be using for training today, but they're very close to field conditions as well. R22 suction pressure about 70 to 75 psi. R22 liquid pressure about 195 to 230 is going to get you pretty close. R410A suction pressure, we're looking for about 135 to 145. And R410A liquid pressure, about 330 to 350 is going to get you really close on our service calls today. Does everyone have this written down that wants it written down? Go ahead and unmute your mic. We'll give you another 30 seconds or so to write this down, then we'll talk about the other parameters. So remember, a unit with an expansion valve, about 10 to 14 degrees of superheat, subcooling about 10 to 14 degrees. Unit with an orifice or a piston on the indoor coil, you're going to have to look at the superheat chart to find out what the superheat is supposed to be. Subcooling should run about 10 to 14 degrees with an orifice as well. Now please refer to the bottom of the chart right now as we talk about temperature drops across key components in the refrigeration circuit. And team, I'm going to ask that you kind of keep this parameter sheet handy when we do our service calls. You should have a handout that you're making some notes on, and kind of keep this handy when we're doing our service calls. So the maximum temperature drop we're going to allow on a liquid line today between the two liquid temperature probes is going to be 8 degrees Fahrenheit. That's the maximum temperature drop we're going to allow in the liquid line. If you see a temperature drop larger than 8 degree difference between the two temperature probes on the liquid line, you'll consider that liquid line kinked or restricted or undersized, and that's the problem with the unit. So be sure and look for that liquid line temperature drop not to exceed 8 degrees. The maximum temperature drop we're going to allow on a suction line from the evaporator to the compressor is 3 degrees Fahrenheit. And the reason that's such a different number than the liquid line is because that's the real big line that's well insulated, so you shouldn't have any temperature drop across there at all, but we will allow up to 3 degree difference. And by the way, this is very much industry standard for diagnostics. The maximum temperature drop we're going to allow on a filter dryer, on any filter dryer, will be 3 degrees Fahrenheit. So as you take a look at our refrigeration cycle diagnostic screen here in a little bit, you'll notice we have temperature probes on both sides of the filter dryer. If you see any more than 3 degree temperature difference across that filter dryer, you will consider that dryer restricted, and it'll be coupled with low suction pressure and other things as well. So the parameter sheet that we're just talking about right now, again, kind of keep this off to the side to kind of remind you what the pressures should be, are close, and temperatures of drop key components. Any questions or comments on the parameter sheet before we continue? Okay. All right. The next little sheet we're going to overview is our diagnosing system problems for AC. And these are classic, typical service scenarios. And so let's do one real quick. And please keep this little handout off to the side to kind of jar your memory as well as we start doing some service calls together today. So a classic service call, you may have a low refrigerant charge. So if you have a low refrigerant charge on your system, your coil conditions will come out, it'll just start screaming at you, so to speak. You're going to have high superheat on the evaporator if you have low refrigerant charge. You're also going to have low subcooling on the condenser. So what that really means, if I have high superheat on the evaporator, that coil's starved. If I have low subcooling on the condenser coil, that coil's starved. In addition, you'll have low suction pressure and low liquid pressure. So if all of our pressures are low, and we have low subcooling and high superheat on the evaporator coil, we know we have a low refrigerant charge. Now on this sheet, make a little note someplace. If you have a situation where it looks like a low charge, double check your suction line, your suction line from the evaporator to the compressor, because if that has a kink in it, it'll look like a low charge. So maybe make a little note of that, a little mental note of that. If you have a suction line restriction, you're going to find that it's going to look a lot like the same conditions as a low refrigerant charge. And you're going to find that by the temperature drop across the suction line on those components. Let's do another one that's really, really close. We're not going to go over all these. You can kind of read them, but keep your diagnosing system problem page kind of off to the side too when we do these service calls. It'll help jar your memory. If you have a low heat load on the evaporator, a low heat load, a technician may think this is a low charge because he has low subcooling, low suction pressure, low liquid pressure. But hang on a second. With a low heat load, in other words, we don't have enough airflow on the evaporator, and it's icing the evaporator up. We're not getting the proper heat flow or the proper airflow. It'll also drive the superheat low. So unlike a low charge, a low heat load is everything is low. Low superheat, low subcooling, everything is low. Low suction pressure, low liquid pressure. And a technician, if he hasn't had this type of training, he'll start adding refrigerant. And it just makes it worse because he's not changing the airflow, or he hasn't provided that low load condition. He hasn't corrected that low load condition on the evaporator. And the way you tell that is everything is low on the evaporator for low heat load. One more that's kind of common out in the industry is overfeeding TXV, or if you have an oversized piston or orifice. What that'll do, it'll give you low superheat. In other words, it floods the indoor coil, the evaporator. Low subcooling because it empties the outdoor coil. It drives the suction pressure high and the liquid pressure low. So by looking at all these conditions, team, on our service calls coming up, by looking at superheat and subcooling to find our coil condition, by looking at our suction pressure and our liquid pressure, and then looking at the temperatures throughout the refrigeration circuit, we can diagnose system problems very, very, very quickly. And so that's what we're going to be doing next. We're going to do some service calls next and give everybody the opportunity to do some service calls together. And so we're about 1 hour into the program right now. And so let's take another half hour or so and we'll do some service calls and we'll just see how everybody does. And certainly keep your mics open and questions ready as we do these service calls together. So looking at our first service call screen, we see that it's an R22 unit. We have white background on the gauges. In addition, we see that we have an orifice type of metering device. So in this example, excuse me, we should be looking at our superheat chart to find out what our superheat should be. So let's do that together as an example. So we see that we have an indoor wet bulb of 76, an indoor dry bulb of 81, and a relative humidity on the indoor coil of 80%. So we have an 80% relative humidity. So we automatically know that we're going to be using the red wet bulb lines because we have a relative humidity of 80%. So as we take a look at that, we see our wet bulb temperature is 76. So on your superheat chart, find 76 or close to it. I see that there's a 75-degree green block on my indoor return air temperature. So find 75. And we have an outdoor air temperature of 92 degrees. So find that 75-degree wet bulb temperature and then go down and correlate 92-degree outdoor air temperature. And tell me, team, what should my superheat be under those conditions? Anybody off the superheat chart?
24.
That sounds about right. Good, excellent.
That sounds about right. Good, excellent. So write that down and remember it. So about 24 degrees of superheat is what it should be. Now let's go ahead and find out what our superheat actually is. So referring to your pressure temperature chart, we have 109 pounds of suction pressure off the pressure temperature chart for R22. And so what is the pressure temperature conversion of 109 pounds of pressure off the pressure temperature chart for R22? What's the
64.
pressure temperature conversion?
Okay, good. And we noticed it on our...
Okay, good. And we notice it on our suction line leaving the evaporator coil. It's 65 degrees, so we only have 1 degree of superheat. So for whatever reason, my superheat is very low, and that indoor coil is flooded, absolutely flooded. Now we know it's low superheat for 2 reasons. Number one, we never charge below 5 with a piston. But looking at the superheat chart, that first step we took there, we see that it's supposed to be about 24 degrees superheat, but we only have 1 degree of superheat. So we know our superheat's extremely low on the indoor coil. Let's keep working. So low superheat, write that down and remember it. The next thing we're going to look at, let's go ahead and look at our condenser coil condition. We have 192 pounds of pressure on the liquid pressure. And so if we convert 192 on the R22 chart, 192 to temperature, what is our pressure temperature conversion at 192?
Be 99.
Sounds about right, 99 degrees. And we take a look at our temperature probe on the outlet of our condenser coil. We have 97. So we only have 2 degrees of subcooling. So in this example, we have low subcooling and low superheat. Let's translate that. The outdoor coil is absolutely starved. The indoor coil is absolutely flooded. Now, referring to your little parameter sheet that we talked about, tell me, anyone, is the suction pressure high or is the suction pressure low for an R22 system? Okay, we see the suction pressure is very high. Now remember, an R22 system under normal running conditions off your little parameter sheet that we gave you should be somewhere between about 70 and 75 pounds of suction pressure. But we see that it's 109, so we have high suction pressure. We also notice that our liquid pressure on this call is 192. It's 192 pounds of liquid pressure. And on an R22 system under nominal running conditions, it should be somewhere around 225, about 195 to 230, something like that. So our liquid pressure is low, suction pressure is high, superheat's low, subcooling is low. So under those conditions so we have high suction pressure, low liquid pressure, low superheat, low subcooling. What's the problem?
Overfeeding, oversized or whatever.
Excellent. Give yourself a star. Oversized orifice. So whatever reason, maybe this is the initial install, and they got the wrong piston in. And sure enough, I'm flooding the indoor coil, emptying the outdoor coil. driving the suction pressure up and driving the liquid pressure down, it works every time. Any questions or comments on that first service call that we did? Okay, let's do another one together as a class. So in this example here, we see we have an R22 service call and we have an expansion valve. So automatically we don't have to look at the superheat chart because the expansion valve should maintain about 10 to 15 degrees of superheat. So let's go ahead and let's find out what our superheat is on the indoor coil. So step number one, we look at our suction pressure. And we have 76 pounds of suction pressure. R22, what's the pressure temperature conversion at 76 pounds of pressure for R22?
45.
Okay, good. And the temperature leaving on the suction line leaving the evaporator coil is 55. So that gives us 10 degrees of superheat. So that's actually about normal. So the indoor coil is about normal. And let's keep working. At 325 pounds of liquid pressure, what's the pressure temperature conversion for 325 pounds of pressure for R22? Anybody?
137.
Okay, 137. Now, as we take a look at the temperature of the liquid line leaving the outdoor coil, we see we have 102 degrees. So the difference between 137 and 102 is about 35 degrees of subcooling. So what's the condition of that outdoor coil? Is it flooded, starved, or normal?
It's flooded.
Okay, good, excellent. So the outdoor coil is terribly flooded. Indoor coil is about normal, which tells us the expansion valve is working okay. The expansion valve is functioning because it's holding that liquid pressure back, and it's maintaining a superheat of about 10. It's also, that expansion valve is also helping maintain about a normal suction pressure. So what condition would give us high subcooling, high liquid pressure, about normal superheat, and about normal suction with an expansion valve system? About normal superheat, about normal suction, high liquid pressure, high subcooling with an expansion valve system. What's your diagnosis?
Ty says overcharged.
Excellent. This is a classic overcharge with a functioning TXV. That's exactly. Yeah, there you go. Give yourself a star on that. And so remember, team, we're charging systems with an expansion valve with the subcooling method of charging. And so we're looking for about 10 to 15 degrees here, but we have over 30. And so that tells us, that the expansion valve is working because it's maintaining a superheat level and a suction pressure that's pretty close to normal. But the head pressure is out of control, and we have way high subcooling. So this is a classic overcharge with a functioning TXV. Good. Give yourself a star. That was an excellent diagnosis. Okay, let's try this one on for size. We see that we have an R22 system with an expansion valve on the indoor coil. As we take a look at those pressures are pretty wonky. We've got low suction pressure and elevated, not super high, but elevated liquid pressure. So as we take a look at the pressures and the temperatures throughout the refrigeration circuit, tell me, is anything jumping out at anybody?
The dryer temperature differential.
Very good. There you go. So we have a restricted dryer. Now, before we move away from this screen, let's talk about this for just a second. If I have a restriction in the dryer, would it be flooding or starving the indoor coil?
He's starving the indoor coil.
Yeah.
Sure. And if we did our superheat right now, we'd see that we've got about 50 degrees of superheat or more, and so that proves that out. In addition, if I restrict that dryer, would it cause the suction pressure to go up or the suction pressure to go down?
Down.
Excellent. So we have low suction and high superheat, which is a classic example of some sort of liquid circuit restriction. And then if we start looking at our temperature probes, we find that sure enough we've got a big temperature drop across that dryer. So that was an excellent diagnosis. Now, one of the things I'm going to encourage everyone to do and to train and to talk about, when you have opportunity to talk about this in the field or with your customers, is that these temperatures that we're taking, or the yellow temperature blocks, those are just minimum temperatures that we want you to take when you're doing air conditioning diagnostics. So now if we want to have temperatures across the suction line, we want to have temperatures across the liquid line, we want to have temperatures across the filter dryer, and these are minimum temperatures. Now if the contractor wants to take 5 readings across the liquid line, that's perfectly fine. If he wants to take 4 readings on the suction line, that's perfectly fine too. These are minimum readings that we're showing you on our refrigeration diagnostic screen here. Any questions or comments so far? Well, so far I haven't been able to stump anybody. Let's do a few more service calls. In this service call here, we see we have an R410A service call, and it's featuring an expansion valve. And as far as the temperatures across the refrigeration circuit, nothing's jumping out at me, so let's go ahead and work this through. Let's look at superheat, let's look at subcooling, let's look at temperatures, and figure out what's going on with this system. So, step number 1, let's go ahead and find out what the superheat is. So I have 170 pounds of suction pressure. And so referring to your R410A chart, what's the pressure temperature conversion for R410A at 170 pounds of pressure? Anybody.
60.
About 60. Good, excellent. Now we also see that our leaving the indoor coil, the evaporator coil, we have 61 degrees suction line temperature. So suction line temperature is 61 degrees, and so we have a low superheat value, and so that means the indoor coil is flooded for whatever reason. So write that down, low superheat flooded coil for whatever reason. Now let's take a look at our high side, our condenser. Let's look at our subcooling on the condenser in this condition. At 282 pounds of pressure, what is the pressure temperature conversion at 282 off the 410A chart?
92.
About 92. Good, excellent. Now we notice that over here, leaving the condenser coil, we have a 90-degree liquid line. So we only have 2 degrees. There you go, it's starved. So the subcooling is low. We have a starved outdoor coil. The superheat is low on the indoor coil, and so we have low superheat. Suction pressure is elevated. We should, normal is going to be about 130, 135, something like that on 410A. So suction pressure is high. Liquid pressure is low. It should be 320, 350, somewhere in that range. So suction pressure is high, liquid pressure is low. Subcooling is low. Superheat is low. So I've got a starved condenser, a flooded evaporator. Suction pressure is high, liquid pressure is low. What's your diagnosis? Superheat low, subcooling low, suction pressure high, liquid pressure low. So referring to your diagnosing system.
Overfeeding the TXV.
Ooh, I love that answer. So we have an overfeeding TXV. In other words, that thing is stuck wide open for whatever reason. Now, team, maybe make a note of this from a field standpoint, a little field tip. A lot of times an expansion valve will overfeed, especially if it's been in service for a while. If it's on initial install, they may have damaged it when they installed it by overheating the sensing bulb. That'll cause them to overfeed. But if it's been in service for a while, sometimes that sensing bulb will get some corrosion under it on the sensing bulb where it clamps onto the suction line. So I can't tell you the number of service calls I've been on, not only air conditioning but also refrigeration service calls when I did commercial refrigeration, where if you take the sensing bulb off the suction line and clean it really good, and clean the suction line where it clamps on, clean the suction line real good, and then clamp that sensing bulb back on good and securely, and then insulate it with some Armaflex or whatever and insulate that bulb, it'll cure that problem. So a lot of times with an expansion valve system, if it's been in service for a while, the sensing bulb has just got some corrosion under it, and or maybe it's sitting there loose, and it'll look like this. It'll cause this situation, overfeeding condition, especially if it's been in service for a while. If it's a brand spanking new installation, the chances are if it's overfeeding on a brand new install, the installers maybe had overheated or heated the sensing bulb, and it damaged the power head, and it caused that valve to flex and stick open. So just kind of keep that in the back of your brains. If it's been in service for a while, clean the sensing bulb. If it's brand new install, double check to make sure that the sensing bulb did not get overheated. But either way, if it's stuck, beating on it with a hammer is not going to help very much. And so we recommend that if it is overfeeding, go ahead and replace that valve if you've tried those other service procedures. Any questions or comments on this overfeeding TXV condition? Okay, well, let's do a few more service calls. In this example here, we have an R410A system, and we see that nothing is really jumping out at us on the temperatures as far as a kink liquid line or anything like that. So let's go ahead and work the problem. We have a TXV, so we're looking for about 10 to 15 degrees of superheat would be considered normal. And so at 102 pounds of pressure on this 410A unit on the suction side, what is the pressure temperature conversion at 102?
About 33.
On the suction. About what is it again?
About 33.
Okay, about 33. Okay, good. Now the temperature on the suction line is 54 degrees. So we have over 20 degrees of superheat. And so that tells us the indoor coil is starved.
Yeah.
All right, so let's keep working at 256 on the liquid side at 256 pounds of pressure. What's the pressure temperature conversion at 256?
About 85.
Okay, good. So we see that our subcooling is low, our superheat is high, our suction pressure is low, and our liquid pressure is low. So in this example here, all of our temperatures look okay in the refrigeration circuit, but superheat high, subcooling low, suction pressure low, liquid pressure low. So what condition would give us high superheat and everything else is low off your diagnosing system problems page?
Low refrigerant?
That looks like a low charge. Yeah, it looks like a low charge. Now remember, team, if I think I've got a low charge, I always want to look at the suction line to make sure I don't have a big temperature drop across the suction line. So if I have two empty coils, superheat high, subcooling low, suction pressure low, liquid pressure low, I always want to double check that suction line to make sure I don't have a big drop across it because it'll mimic a low charge. But in this example, we only have 1 degree temperature difference across there, so I think that's a pretty good diagnosis. That's a classic low charge condition. Any questions or comments? I'll tell you what, everyone's doing really good. I sure appreciate the interaction too as we do our session today. All right, let's take a look at this one. We notice this is a 410A unit with a piston on the indoor coil. And so as we take a look at this, we remember now we have a piston or an orifice on the indoor coil, so we need to find out with our superheat chart what the superheat should be. So let's do that first real quick. We see that we have an indoor dry bulb of 78, an indoor wet bulb of 67, and we have a relative humidity of 55% on the indoor coil, on the return air. So as we take a look at that, we automatically see at 55% relative humidity, we're going to use the dry bulb number, So we have 78 degree dry bulb. Well, I don't have 78 degrees on my chart, but I've got pretty close. I can go 80 degrees. So 80 degree dry bulb, that's pretty close, and 90 degrees outside. So 80-degree dry bulb, 90 degrees outside. What should my superheat be under those conditions?
13.
About 13 or 14. That's close enough. So now let's find out what our superheat actually is and compared to what it should be. So we have 142 pounds of suction pressure. What's our pressure temperature conversion for 410A at 142
About
pounds?
50.
Okay, about 50. Good. And we see that we've got 61 degrees of suction line temperature. So our superheat level is about 11, about 10 to 11 degrees of superheat. And so what would you consider the condition of that coil? We're looking for about 12 to 13, but we've got about 11 or 12 degrees of superheat. So what's the condition of that coil? About what? Looks like it's about normal. So with that piston, under those conditions, it looks like our indoor evaporator is about normal. So let's keep working. At 342 pounds of pressure on the high side, what's the pressure temperature conversion for 342 off the 410A chart?
About 105.
Okay, about 105. And as we take a look at our temperature on our liquid line coming out of the outdoor coil, we see we have about 96, which is going to give us about 9 or 10 degrees of subcooling. So the subcooling is about normal. Looks like the superheat is about normal. Suction pressure is slightly elevated, but within normal ranges, and liquid pressure is about normal. So what's your diagnosis on this one? Superheat looks about normal, you said. Subcooling's about normal. Suction pressure is slightly elevated, but within normal ranges. It's 90 degrees outside after all. And about 342 pounds of liquid pressure. If you take a look at your parameter sheet, that's fairly close to normal. So, and liquid line, dryer, suction line look about normal. So what's your diagnosis? Superheat about normal, suction pressure about normal, subcooling close to normal, head pressure about normal. What do you think's going on with this? Well, team, you got to recognize normal too, don't you? Any questions or comments?
Yeah, I mean, nothing stuck out. I was looking at it.
Well, we did that one on purpose because we wanted to make sure that, sometimes, you get on a job site, everything's looking pretty good. So while you're there, you do a clean and check. You clean the coils and change the filter and check electrical connections and all that stuff. But I mean, if I get on a situation like this and everything looks good after I've done my cleans and my clean and check and all that stuff, if it looks normal, it is normal if it's running normal. So we need to recognize normal as well. Any questions on that? Okay. Well, let's see how many more service calls we have. That may be our last service call because a lot of times I like to conclude on a normal service call, but I'm pulling them kind of randomly on the screen here. And so we may have a few more, or that may be the conclusion of that. But either way, is there any questions or comments so far on what we've trained on today? Is everybody good? Okay, let's see if we have any more on this one. Okay, looks like we do have a few more service calls. So we'll go ahead and do a few more service calls. Like I said, looks like I randomly threw a normal one in there for you today. Okay, so on this service call here, we see we have a 410A unit, and we have a TXV on the indoor coil. And so as we take a look at it, one of the things that's jumping out at us, we see that our suction pressure is low, And our head pressure, our liquid pressure, is also low. But let's go ahead and work this system, or work this problem through. Referring to your 410A chart, your pressure temperature chart, tell me, team, what's the pressure temperature conversion for 98 pounds of suction pressure?
$31.
About 31. And we notice that the suction line temperature leaving the evaporator coil is 33, so we have low superheat to start with. How about at 247 pounds of pressure? What's the pressure temperature conversion at 247 off the pressure temperature chart for 410A?
About 83.
Okay, and so we take a look at our outdoor coil. We have 83 degrees of subcooling, and our liquid line is 82. So we only have about 1 degree of subcooling. So in this example, our superheat is low on the indoor coil. Our subcooling is low on the outdoor coil. Suction pressure is low. Liquid pressure is low. Everything is low. Now, the refrigeration components look fine. I mean, it doesn't look like we have a kink in the liquid line or the dryer. The suction line looks okay. But we have low suction pressure, low liquid pressure, low superheat, low subcooling. In other words, everything is low. What's your diagnosis?
That'll be your low heat load evaporator.
Excellent. So some examples of a low heat load, give yourself a star. Some examples of a low heat load would be a dirty evaporator coil. Or maybe it's an undersized return duct. Or maybe you have a dirty air filter. Now the most likely cause is just a dirty air filter. You have poor airflow. So anytime you have low airflow on the indoor coil on an AC system, it's going to drive the pressures down. It'll also drive the superheat and subcooling down. So if everything is low, it's not a low charge, it's a low heat load on the evaporator. And quite often you'll actually see that the suction line is really sweating, or maybe it's even frozen. And you'll see ice building up on the coil and stuff under these conditions. So we see that, we have a low heat load, and the number one cause for low heat load is a dirty air filter on the indoor coil. Probably number 2 and 3 right behind that is going to be a dirty evaporator. Maybe the evaporator just needs to be cleaned. Or you have an undersized return duct, or maybe the homeowner has thrown a rug over the return grill. We've seen that happen as well. So just remember, low heat load is always going to indicate low airflow on the indoor coil, and that's what we're going to be looking for whenever we see these conditions on the refrigeration circuit. Any questions or comments on that? Okay. Well, team, let's take a look at this one, examine this one, and can anybody tell me what's really jumping out on this one as far as a problem?
Your suction pressure and liquid.
Okay, suction pressure is low, and someone said something about the liquid line. Is that correct? Okay, so again, on this service
Looks like
call,
you got a kink in the line.
There you go. And so if we have a kink in that liquid line, it's going to be indicated by a big temperature drop across the liquid line. And anytime we kink that liquid line, what it's going to do, it's going to drive the suction pressure low, because we're starving the evaporator, and that compressor is trying to suck against that restriction. And so the suction pressure will be low. Liquid pressure will be elevated because we're backing all that liquid up into the condenser coil. That's going to drive the subcooling up as well. So this is a classic liquid line restriction, and with low suction pressure. So whoever said liquid line and suction pressure, give yourself a star. This is a liquid line restriction. Absolutely. Okay, here's a R22, just to kind of give you a little variety, team. And so let's go back to our R22 pressure temperature chart. We don't see anything jumping out at us anywhere on the in the refrigeration circuit. We've got an indoor dry bulb. Oh, excuse me.
Well, your suction pressure is low.
Okay, good. Suction pressure is low. Excellent. And so let's work the superheat on the indoor coil. So I have 31 pounds of suction pressure. What's the pressure temperature conversion at 31 pounds of pressure for R22?
9.
Okay, about 9. And we see the actual temperature of the suction line itself is 61 degrees, so we have very, very high superheat. We've got 48 degrees of superheat, something like that. So the superheat is high, suction pressure is low, liquid pressure is elevated. Let's do our subcooling real quick on the outdoor coil just to confirm that we've got high subcooling. So at 227 pounds of pressure for R22, what's the pressure temperature conversion at 227?
111.
Okay, so 111. And so we see that we have high subcooling. We're looking for about 10 to 15. And we see that we've got, so 111 would be about what, 20 some, almost 20, 22 degrees of subcooling. So our subcooling is high. Suction pressure is low. Superheat's high. So what in the world would give us a condition of low suction pressure, high superheat, elevated subcooling? This looks an awful lot like a liquid circuit what? This is kind of a tough service call. All right, so let me give you a little hint. This is a liquid circuit restriction, but it's not in the liquid line. It's not in the dryer, but we know it's a liquid circuit restriction because the suction pressure is low, subcooling is elevated, and superheat is off the chart. It's way high. Suction pressure low, superheat high. We start looking for a liquid circuit restriction. This is a liquid circuit restriction, but it's not in the dryer. And it's not in the liquid line. So where's the next logical place for that liquid circuit restriction to be? Anybody?
Would it be anywhere closer to TXV? I'm guessing just liquid, but
That's a good diagnosis. So a restricted TXV will look just like this. It'll drive the suction pressure low. It'll drive the superheat high. But if we take temperatures across the liquid line looks fine. And if we take temperatures across the dryer looks fine. And so the next logical place in that whole liquid circuit for a restriction would be the TXV. So good. It's kind of a process of elimination on that one. So that was an excellent diagnosis. Any questions or comments on that? Okay. Whoop. I gave that one away. Hold on. Let's do this one together. This is an R410A system. And we've got 112 pounds of pressure on the suction side. And 277 on the liquid side. So as we take a look at this together, we have an expansion valve. So we're looking for 10 to 15 degrees of subcooling and about 10 to 15 degrees of superheat. Nothing's jumping out at us on the dryer or the liquid line.
you got a low suction and low liquid pressures.
Okay, low suction and low liquid pressure. Excellent, excellent. Well, let's take a look at the superheat on the indoor coil then. At 112 pounds of pressure on the suction side, what's the pressure temperature conversion for R410A at 100?
39.
Okay, and we take a look at the suction line temperature, it's 38, so we only have 1 degree of superheat. And then as we take a look at our outdoor coil, the condenser coil, we have 277 pounds of pressure on the liquid pressure. So what's the pressure temperature conversion for 277 for 410A?
91.
Okay, good, excellent. So as we take a look at our screen, we see that we've got about 2 degrees of subcooling, We have about 1 or 2 degrees of superheat, so subcooling is low, superheat is low, suction pressure is low, liquid pressure is low. All the refrigeration components look fine. It doesn't look like we have any kinks or anything anywhere. All the temperatures look okay. But our superheat's low, suction pressure's low, liquid pressure's low, subcooling is low. In other words, everything is low again on this particular service. What's your diagnosis?
Be another low heat load.
I like that. I'll tell you what. I can't stump you guys. Well, give yourself a star. Good. Okay, let's see how many more that was our last service call. Well, fellas, I'll tell you what, before we conclude for the day, let's go ahead and open the mics up and the floor up for any final questions or comments. Good job on the service calls, by the way. You guys, I wasn't able to stump you on the service calls, which is great news. That means that we're getting the information across to you okay. But before we conclude for the day, and before we hang up, I want to thank everybody for your attendance, but also, is there any final questions or comments on our air conditioning diagnostics program that we did over the last couple days and basically 4 modules? Is there any questions or comments that I can address for you?
Will there be like examples of these things that we probably, like if we wanted to practice and stuff on that we have access to?
I could maybe give you some examples, but what we're doing, we are recording all of these sessions, and so what I'm going to recommend you do is Jill will be sending you the recorded link of our training, and then of course you can review that as much as you like, and then like I said, I could maybe put together a little PowerPoint with some practice sessions or something, but I think that you'll find that if you go over the recorded sessions and we do them all and you listen to them, I think you're going to have a pretty good grasp of what we're doing. But please let Jill know if we need to put together a little something to where you could just practice some sessions with a few PowerPoint slides or something like that. We could do that for you as well. Good question. Is there any other good questions or comments before we conclude for the day?
Nah, I think I'm good, but thank you, Joel.
You're welcome. Well, thank you very much for attending, everyone, and we'll go ahead and secure for the day then. I want to thank you for your time and your attendance today, and we look forward to training with you again sometime soon. Have a great afternoon. Thank you.